Okay, great. So, hi everyone, and thank you for being here or being connected to here. And of course, thanks to May for inviting me and helping me to shape my ideas. What I'm going to talk about is my, let's say, personal experience as, among other things, I'm a coder and I'm a painter. I'm here and then, and this is kind of a personal research project that I want to share with you. So, we're going to talk about tessellation, and I guess how many of you knows about tessellations? Okay, so. And I will have a very, very basic and visual, because I'm a painter, crash course on tessellation, so we know what we are talking about. And the basic is, we are, tessellation is a way of covering a space, a 2D space, to make it simple, with tiles. So it is entirely, you have one or more, let's say, unit repeating, trying to cover. And here you have some hexagons I sketched, because as soon as we think about tessellation, when your mind, at least my mind goes, okay, how many tiles? Is there regularity? Is there a period, pattern? Is there something I can do to change and find some new things, some new vision? And one interesting point to be made is that tessellation could be infinite. You can cover the plane periodically, the whole plane. Of course, this is an abstraction, because in reality, you're always talking about finite tessellation. But if you think, it's easy to visualize how the tessellation can continue forever. And this is one of the reasons why tessellation has been found in human history before any, let's say, formal math definition. Because this repetition, large repetition of very small unit elements, is a kind of direct, very powerful visual approach to the concept of infinity. So, you wonder, you see that you could fill the whole space and take the whole time to do so. So, it is a kind of, let's say, visual cue to something very, let's say, powerful and moving inside us, infinity. And personally, I can feel a very strong personal bond to the craftsman, artisan, philosopher, I would say, that built this floor 2,000 years ago in a Roman villa in Coimbra, in Portugal. This is beautiful and moving. Of course, and this is, let's say, the last slide in this very brief course, tessellations comes in a variety of shapes, and we're not bound to polygons. Here you have edges, parabolic edges, cures, and very, very, let's say, complex things can arise from, let's say, simple tiling. I took this example for two reasons. One, it is beautiful. I mean, these are just two tiles put together. And the other is that this kind of tessellation has been discovered in the 70s by Roger Penrose, so a mathematician, physicist, and by the way, a Nobel Prize winner. So, I mean, we can stay, I mean, it's a comfort when we sketch our little things, I mean, we are in good company. So, then, these are tessellation, and let's say the first, I mean, one side of my research is being writing software library in Scala in a functional style, and it is a free resource, it is public, and you can find it on this website, and it is freely available. It's a work in progress. It welcomes, of course, let's say, contribution. And it is interesting for me that Scala has quite a large footprint in terms of diffusion. So you can port it to Java, to JavaScript, and if we have time, I will show you a little bit of JavaScript. What is the goal of Tessella? By the way, Tessella is the Latin name word for small tiles. So it is also the English, the root of the English word tessellation. So I thought it was a nice name for the library. The purpose is to provide a toolbox of functional methods that deals with finite tessellations, and restricting ourselves for the time being to the most classical form of tessellation, which is tessellation made by regular polygons. So using just a square, a regular triangle, and so forth. The main, let's say, point behind the library is that tessellations, finite tessellations, are described as undirected graphs. And so, every tiling is an undirected graph, which is a powerful way, computational model, to deal with these objects. Of course, not every undirected graph is a tiling. So this is where things get mathematically, let's say, a little bit complicated. In this example, of course, 3 square and a regular pentagon cannot exist in a regular tessellation, because the vertex configuration at node 5 is more than a full circle. And so this is let's say, a nice graph, but not a tessellation. And we have to factor in also spatial requirements, because this could be a tessellation, but it is overlapping. So, once again, it is not okay. So, in Tessella, we provide, let's say, a validation check and functionalities to let's say, check the validity of the regular polygon tessellation. And the milestone so far is that we have transformation functions that allows very basic functionalities, like adding or removing one regular polygon at a time. And we can test equality among finite tessellation, that they mirror it, the labels are different, fine. We know that they are the same. And of course, there is a good wealth of creation algorithms. One line of code creating complex things from basic primitive methods. And we have conversion to visual, because as soon as your undirected graph gets a little bit complicated, you lose sight of what is the visual of the tessellation. So, I mean, nice transformation to SVG, and conversion to graph description languages, so you can have your graphs factoring by other application. And let's say testing of values of the tessellations that can help us in our, let's say, search methods for interesting things. The main point for me on the artistic side of the research is being able to write this basic transformation function, because these are, let's say, what I needed to start experimenting with random things and, let's say, feeding methods to see what happens without having to start from, let's say, describing a pattern, but making a pattern in the way. So I needed methods to say, I want to deal with finite things, I want 5 squares or 100 squares. I want to describe this mathematically, having a computational model, so I can add one another polygon and see what happens. But the toolbox is there. I mean, it's there for mathematics, it's there for whatever you want. And for me, the direction, I mean, my sensibility was art. So I was interested in seeing new things and seeing how they could develop. So these are the kind of painting, acrylic paintings that I do is completely, let's say, different realm from coding, because I stopped coding and I started doing things. It is hard work because I try to stay, in coding as digital as possible and in painting as analogic as possible. So I get my pencils and a compass and I sketch and paint. And that's, it is satisfying work, also it is kind of meditation work in the process, and I'm pleased about the results. I like what I do. But what I wanted in this realm of regular polygon tessellation, I want to give you a little bit of, let's say, the research path that I went through. For my sensibility, there was a problem of scarcity, because the fact is that when you enter regular polygon tessellations, there are just 4 regular polygons that completely tessellate the whole plane. And one of them, the 5th, is the octagon, it appears only in one tessellation. So you find yourself more or less here. You have all the 4 polygons. It is squares, triangles, hexagon, and dodecagons, 12-sides polygons. And this is the kind of, let's say, unicorn in regular polygon tessellation. You have just 7 of these tessellations, where you have 7 classes of symmetry with 7 different vertex configurations. I don't know if you see it, but each vertex is colored with a different color, and each different color is a class of symmetry. You can move the tessellation from one color to one color, and it remains the same. But you cannot get more complicated or beautiful than this. And for me, it was a kind of boring. I don't like to paint this, okay? It's already that. So I went for using, let's say, more variety of polygons, even knowing you don't fill the whole plane. And so I started playing with randomic growth. First with polygon tasks. So what if I take pentagons and decagons and grow them? And then I started putting more constraints. So what if I take pentagons and decagons and I want vertex configurations? And things starts to appear, and then you have an artistic limit. I mean, you don't. You take what you feel is right for you, and I think as an artist you are allowed, let's say, freedom to bend the rules. So this is not more a regular polygon tessellation, even though it is a tessellation. I mean, if you think at gaps as regular polygons, we are still in the realm of tessellation. It is not a regular polygon tessellation, but it's nice to me, so I painted it. And so I went on, and these are more examples for this. And that's it. That's my research, my pet project, and my fun pastime when I have time, and I'm happy that I've been able to share it with you. And of course, if you have questions now or afterwards, I'm here for you to answer.
The style of tessellation that Escher uses, for instance. Have you tried experimenting with that?
No, not yet, but I mean, in terms of coding, we are talking about functional codings, and once you start seeing tessellation as graphs, it is just a matter of which constraints you want to apply to your graph in order to get, let's say, different classes of tessellation. So that's definitely is a kind of research path that could be followed.
Thank you for the talk. We were talking before about more possibilities for the development of the cell, and I talked on another one that might be interesting. Do you know the work of initiation? You probably seen this tessellation of the circle. Then if you allow in abstraction for the space to have some kind of curvature, then you can play, like you can have an heptagon tessellation, which would be really fun. And I think the representation might be as well, because you are when you see the graph is like abstract from any kind of distance notion, so you will still have the same representation and start, I don't know exactly how, probably play with curvature of spaces.
Yeah, definitely. And also, I started experimenting also on, let's say, 3D tessellation, so feeling of the 3D space, and that's again, it is something very interesting artistically. I have some ideas of, let's say, sculptures that could be 3D printed, that is very digital, or could be handcrafted. This is very logical, but very heavy stuff as well.
And just a quick technical fast question, like when you output image, what kind of control you already have on the position of the image, maybe the colors you have?
Okay. I don't know if we have time, but I can, let's show you a little bit. I was talking about, let's say, JavaScript. So this is a very, let's say, primitive JavaScript, let's say, things derived from the library. I can randomize, and in terms of control, I can decide. I mean, it is just an SVG file, so you have all the controls that you want. But you can hide, put, let's say, randomize again, and this is it. Or I can say, give me quantity of band, randomize again, and that's it.
It actually wasn't good with the state. The might's not for the might's for the people on the project. So it needs to be a little higher.
Okay. Okay, sorry.
We have time for one last question. We started at 15 full minutes. Like, we're not going to worry about next break.
By the way, this is fantastic. Unbelievable. I don't know if you can quite see the shirt, but this is actually a minimum spanning tree of an aperiodic tiling done by Dr. Edmund Harris. So my question is, do you have collaborators in tessellation, Tessella, and things like this? Are you looking for some?
Not really. I mean, I'm looking for contributors on the library. I mean, definitely, in terms of, let's say, spreading the beauty, I mean, I'd love to have, let's say, collaborators and peers. And that's one of the main reasons I decided to step up and come here. I mean, to meet like-minded people. So if you are interested.
Great, yeah, we should talk more after this. That's his specialty, is tessellations, tilings, aperiodic, things like that, bringing that to 3D, and there's much more to it. This is fantastic.
Great.
What a wonderful note to end on. Let's thank you again.